All right, good afternoon, everybody. Let's get started. So today we're going to first finish off the few slides from last lecture about guarded interfaces, and then we're going to move on to hardware synthesis. So from last time, we learned the following things about guarded interfaces. The first is that we can express sequential circuits using these guarded interfaces. And the way that that works is as follows. The first thing is that every method has a guard, or this ready wire. And so if we look at this example of this FIFO method, we see that, FIFO module, we see that all three methods, the first, the DQ, and the NQ, all have this green ready signal, which is the guard. Now, it can sometimes be true by default, but otherwise it can be defined by the guard of the method. In addition, every action and action value method is going to have an enable wire. And then what enable wire has to be set to true in order for the action to actually be performed, but it can only be set to true if the guard is also true. And finally, every method can also have some input data, and value and action value methods can also have output data. So let's take a look at the details of this FIFO example over here and see how all of these rules apply. So as we mentioned, each of our methods has a ready signal. So we've got this ready signal coming out from all three of our methods. We have two action methods, and so both of those are going to have an enable signal. And so we see this red enable signal going into our NQ and our DQ methods. And then our first method is a value method, and so it has data coming out of it. And finally, our NQ has an input parameter, and so this blue arrow here corresponds to the input parameter that the NQ receives. Now, you'll notice that the enable and ready signals that we're showing in this diagram are actually implicit. You're not going to see them explicitly in our interfaces, but you need to make sure that you understand that they're there and what exactly it is that the compiler is going to generate for you. So another example that we saw is this GCD interface last time. And once again, we have, for both of our methods, we have a green ready wire. Because both of our methods are action methods, both of them have an enable. In the case of the start method, we have two inputs, A and B, which we see here in these blue wires. And then the action value method has a 32-bit output, which is shown with this blue wire. And so we saw last time that this is what the implementation of a guarded GCD module looks like. And so in green here, I've highlighted what the guards are for the start method and for the get result method. And so these are going to be used in order to define what goes into these ready signals. All right, so what happens? So a couple things that I want you to note about here. So the first is, in every module, or every sequential module, we have a few different components. So the first is the instantiation of our state, okay? So this part that I've highlighted right here, it tells us that we have two 32-bit registers, both of which are initialized to a value of 0, and we have a Boolean register for the busy flag to tell us whether or not the GCD is in the middle of the computation. Next, we have our start signal, which is going to have the guard that says, you can only call start if my module isn't currently busy. And when you do call it, then it'll take the input values of A and B and assign them to your internal registers X and Y, and it'll also set your busy flag to true. Then we've got this rule which runs all the time, okay? And so what is this rule doing? It's doing the actual computation of our GCD, okay? So initially, when you haven't actually assigned anything to X and Y, your x and y are both 0, and so this execution of this actually has no impact. But as soon as I assign a and b to x and y, then this rule is going to start to do some useful work, and ultimately it's going to find the actual greatest common divisor. And when it finds it, we're going to be in the situation where x is now equal to 0. So once x is equal to 0, then this rule, even though it doesn't have any guards, meaning it's always can fire or can run, it's not going to actually do anything anymore, because it's going to always match this else if statement, which just says, you know, x is not equal to x is equal to 0, so it's not going to do anything. So now finally, because x is equal to 0, our getResult method is able to go ahead and be called. And so we have a situation where both the busy flag is true and x is equal to 0, and so this means that we've completed the computation of our GCD, and so it's now okay for someone from the outside to ask for the result of that GCD computation. So what we do in here is we return our value of y, and we also set our busy flag to false. Now, can anyone tell me what would have happened if instead of setting this busy flag to false as part of my getResult method, I had made it part of my GCD rule, where I had, you know, another else statement that said if, you know, else if x is equal to 0, then make busy be false. What would be the problem with that? Yep.
Would it just keep setting it to false over and over again, which would be kind of wasteful?
That's not actually the problem. The larger problem is that you would have a chance, you would miss the result that you produced, because you would enable a new GCD computation to begin. Okay, so by having it as part of the get result, what's happening is that I'm allowing somebody to get the result of this GCD that I just computed. I then say, after I know that somebody's gotten that result that they wanted, I set this thing, you know, back to false, and so this allows a new GCD computation to start. Okay? All right, so now suppose that I want to make a better GCD module, and I wanted to use the same interface that my original GCD has. So it has the same two methods, a start method, which receives inputs A and B, and a getResult method, which will produce a 32-bit value. But the difference in this new module is that it's going to be faster. And the way that it's going to be faster is that I'm going to make use of two basic GCD modules inside of this module to run twice as fast or get twice as much throughput from this specialized GCD module. And so in order to make that work, I need to add a little bit more hardware. So specifically, I'm adding these two registers, turn I and turn O, which basically do the following. So turn I is telling you which of the GCDs should get the input that's coming into this larger module. And turn O is keeping track of which of the GCDs is the one that's ready to send the output out to the world. Okay? And so together with that information, we're able to every time we get a new request to compute GCD, the first time, you know, we can send it to GCD1, and if we get another one, even while GCD1 is still computing, we can go ahead and now send it to GCD2, and both of those calculations can now be executed in parallel, and so I'm able to compute, you know, results of GCD twice as fast as I was able to before. So what does the code for this, you know, high throughput GCD look like? Well, as I mentioned, the interface is exactly the same, okay? So that doesn't change. But what's going to change is my module definition. So first of all, you know, one thing that's cool to realize here is that in general we can do that, right? We can create different modules that implement the same interface, and depending on how it is that we define the modules, it's going to specify, you know, how much hardware we're using, how fast they are, how much power they consume, and things like that. But ultimately, if you think of it as a black box, they're implementing the same thing. Okay, so what does my multi-GCD module look like? Well, as we said, it has two methods, a start method and a get result method. And the first thing that I need to do is I need to instantiate what state do I have in here. So in order to do that, I'm going to instantiate two basic GCD blocks, and I'm going to call them GCD1 and GCD2. So that corresponds to these two boxes. In addition, I have to instantiate my two registers, turn I and turn O, which just hold a Boolean value in order to tell you which of your GCDs you should be using at any point in time. So what does my start method look like now? So now my start method is going to take a look at turn I, and if it's 1, it's going to call GCD1. If it's 0, it's going to call GCD2. Okay? And then it's going to toggle turn I so that the next time it does the opposite. Similarly, my get result, when turn O is equal to 1, it's going to get its result from GCD1. And when it's equal to 0, it's going to get its result from GCD2. Okay? And once again, it's also going to be toggled so the next time I get it from the opposite. So does everybody see how this new GCD module is going to be capable of computing twice as many GCD computations as the single GCD module? Yes? Any questions about that? All right, terrific. So what we're going to move on to now is hardware synthesis, which is today's topic. And so what we're going to see is, now that we know how to define both these combinational Bluespec functions as well as sequential Bluespec modules, we want to see what exactly is it that the compiler is turning these modules into, as far as what hardware is it producing. So if you're given, you know, the goal is that if we give you a Bluespec module, we want you to be able to, by hand, effectively compile what's the hardware that's going to come out of the Bluespec compiler. So that's the goal of today's lecture. So before we get started, we're going to introduce one new piece of circuitry which we're going to need in order to show you how all of this works. And this is basically, it's kind of like a mux, but it's specialized in the following way. So basically what this is a mux where each value has an associated valid signal with it. And at any point in time, at most, one of my inputs can be valid, and whichever one it is that's valid, that's the one that comes that goes through to the output. Okay? And so what is the logic for X? The logic for X is that if V1 is true, then it's going to get X1, or if V2 is true, then it's going to get X2. And similarly, this output V is going to be true as long as one of V1 or V2 is true, and it'll be false if neither one of them is true. And so now, you know, this is, so basically what this is telling you is that each X of I, both on your inputs and on your outputs, is only meaningful if your V sub I is equal to 1. Okay? And so essentially now your compiler is going to make sure that if you have multiple things coming into this specialized mux, it has to make sure that at no point in time are more than one of those V sub I signals equal to 1. Okay? And so the circuit that this multiplexer corresponds to is the following. You basically translate this logic directly, and so X is V1 and X1, or V2 and X2. V is the OR of V1 and V2, and then keep in mind that if X is actually a multi-bit signal, then this portion right here is going to be repeated for every single one of our bits. Okay? So with that new circuit or new gate in mind, let's go ahead and take a look at what the hardware would look like for this 1-bit FIFO circuit that we've seen already. Okay, so just to remind ourselves, here's the interface for the FIFO. So it's got 3 methods. It's got an NQ method, a DQ method, and a first method, which grabs the first value out of the queue. And then here we've got the implementation of this FIFO. So let's see what the steps are first through an example of producing our hardware, and then we're going to try to generalize that. All right, so the first thing I'm going to do is I'm going to look at my I/O interface. So what does my I/O interface define? It defines the methods that are available to me in this module. So specifically, we said we've got an NQ module, a DQ module, and a first module. In addition, the interface tells me exactly what inputs and outputs are coming into this module, right? So we said all modules have a ready signal. So that's this green arrow coming out of each of the methods. In addition, all action and action value methods have to have an enable signal. So that's this red wire coming into both the NQ and the DQ methods, not the first method, because first is a value method. Okay? Now, anytime a method takes in arguments, then we're going to have data coming into the method, like in this NQ example. And finally, when you have a value method or a value action method, you're going to produce a value, and that's going to become available through this blue wire here, which is your output. Okay, so we start off like this. The next thing we're going to do is we're going to look at our state instantiation in our module. So at the top of our module, what we always have is an instantiation of what state is necessary in order to actually design this module. So in the case of a FIFO, we have 2 registers. We have one which is holding the data itself, and because our FIFO can hold data of any type, it's basically of type T. And then we have a Boolean register, which is just telling you whether or not there's a valid piece of data in your FIFO right now or not. Okay, and so that's initialized to false because initially your one element FIFO is empty. And so we're going to take this the state instantiation, and that tells us that basically we have in our circuit these 2 registers, D, which is of type T, and V, which is a Boolean type, and both of them are going to have both a data input and an enable. Okay? The next thing that we do is we take a look at all of our methods and we see, is there a situation where some variable is being assigned to by more than one method? If it is, then what we're going to do is we're going to add one of these special muxes that we just saw as the controller for that input. So specifically, if we look at both the NQ and the DQ method, we see that in both cases we're assigning values to V, and so we need to somehow be able to select which of the values of V is actually going to get loaded into the V register. Okay? So what's next is now we're going to compile each of these methods. So let's go through this really very slowly, step by step. So we're going to start with the NQ method. So what happens in the NQ method? We see that V is assigned to true and D is assigned to X. Okay? So what is X? X is just the input that came into our NQ method, and so we just pass that directly as the data input to our D register. The enable signal is just the enable of the NQ method itself, and so once again we pass that as the enable of our D register because we always want to enable the writing to the D register if the NQ method is enabled. And what about our ready signal? Does anyone have any idea what our ready signal is going to be from this code? What's controlling our ready signal is this guard right here, okay, which is telling us that this method is only going to be ready to be run when not V is true, okay? And so I'm going to take the output Whoops, sorry, I forgot to show you the part about assigning true to V. So here we assign true to V, and we use the same enable from the NQ enable in order to determine when that input is valid. And finally, we produce the ready signal, which is the inversion of V, and that produces our ready signal for NQ. Any questions about how we did that? Great. So we're going to follow the same manner for DQ. And so basically DQ is a little simpler in that it's only assigning a value of false to V. And so this is going to be our second input to this multiplexer, where the data is false and the valid bit is basically the enable of the DQ method. And then the ready signal is just V itself. And finally, in first, our output is the D signal itself. And so we grab the output of our register, that becomes the output of our first method, and then the ready signal is once again the V signal. Okay? So we went through very laboriously how, we produce these signals, but the idea is that we really want you to understand, as your circuits become more and more complex, how exactly all of these signals are going to be produced by the Bluespec compiler. All right, now we could have rewritten this in the following manner, where all we've done is we've pulled all of the outputs to one side and all the inputs to the other side. And so this more clearly shows you that on the left here, we've got our inputs, which are our enable signals and our data inputs. And on the right, we've got our data outputs and our ready signals, okay? So remember, red and blue are inputs, blue and green are outputs. Okay, so basically this itself is a sequential circuit, and even though we don't actually have any cycles in it, it's still a sequential circuit because it has sequential elements inside it. All right, now imagine that instead of using Bluespec, I wanted to try to express this one element FIFO using a truth table. Well, we're not really going to do this. This is really just for illustration purposes to show that even for something as simple as a one element FIFO, it gets really, really complicated to try to express things as a truth table, right? I mean, think of all the inputs that we've got. We've got enables for each one of our we have enables for our NQ and our DQ methods. We've got data coming into our NQ method. We've got our actual state, which has the current state and the next state. And then we have all of our outputs, right? So if you took a look at, one of these lines, let's just pick, one of them at random. Let's say row 2 here, for example. What is this saying? This is saying that initially I don't have a valid value in my FIFO, and what I want to do now is NQ something, and the data I'm going to NQ is D, and so what's going to end up happening is I'm now going to have something valid with data D, and now let's pay attention also to these ready signals. So once I put something into my FIFO, I'm no longer ready to NQ something because I already have something in my one element FIFO, okay? And so my NQ ready is 0, but my DQ and my first ready are 1 because now that I have a valid element in my FIFO, I can go ahead and both read it as well as DQ it. Okay? The one other thing we wanted to kind of highlight in this truth table is that if you really go through all of the possibilities of permutations of these inputs, you're going to find that you also have some invalid inputs. So who can tell me why these bottom 4 rows are actually illegal? Just pick one of them. Yep.
For example, the bottom 2 are illegal because they have the NQ enable and the DQ enable on at the same time.
Exactly. So my FIFO is not able to do, this particular FIFO is not able to do an NQ and DQ at the same time, and so this is actually illegal. Similarly, if I have NQ ready being equal to 0, it would be illegal to try to enable NQ. okay? And so the main point of this is just that it becomes really, really tedious to try to show this via a truth table. And so our Bluespec specifications are much easier to reason about and to think about which combinations are actually valid and what they're going to produce. Okay, so now let's move on and let's look at another example and see what hardware we would produce for it. And so we've seen this example as well. Basically what we're doing is we're streaming some combinational function. So what do I mean by that? It means that I have a combinational circuit F, and I've got an input queue and an output queue. Let's say these are just one element queues. And so the idea is that I'm going to take my value from my input queue, I'm going to run it through my combinational logic, produce an output, and I'm going to place that into my output queue. Okay? And so the rule that's basically describing that is right here. It's basically saying that F is going to take the value coming out of in queue, and then it's going to enqueue that into my out queue. And after it's done that, it's going to dequeue the element that it's already processed. All right, so let's think about what the hardware for this is going to look like. Well, we already know that our queues have three methods with the appropriate wires associated with them, which we've already seen. Okay, so we've drawn that. And then the next step is to draw our combinational circuit and figure out, well, how is it that it attaches to these queues. Okay, so what is it that's happening in this example? What's happening is that we're taking the data out of the in queue and we're passing it to the out queue. Okay, so as far as our data path is concerned, it's very simple. I'm calling the first method from my in queue, passing that to F, and then I pass the output of that to as the value that I want to enqueue into my output queue. Okay? Well, what about all the other signals? So the next thing I need to think about are the ready signals. All right? Now, in this case, we're talking about more than one module. So what I have to think about is I need to have all of my ready signals true at the same time in order for me to actually be able to do this. In other words, I can't put something into my output queue if I wasn't able to also get something from my input queue, and vice versa. Okay, so what we're going to have to do is we're going to have to take all of our ready signals and AND them together. And so we're going to take our our ready signal from our first method and from our dequeue method of our in queue, and we're going to take the ready signal from the enqueue of our output queue. Sorry, this is very hard to say. And together, these are going to basically tell us when it is that we can actually execute this function. And so this is going to produce the enable for both the enqueuing into my output queue as well as my dequeuing from my input queue. Okay? So the idea is we want you to really get a sense for how all these ready and enable signals fit together and what logic is produced as a result of what the particular constraints of your module are. Okay. So, and just one little thing to notice here is that in addition to actually making sure that we took the AND of all of these ready signals, it's also still the case that the enqueue of the output queue is never enabled if the ready signal is not true, and similarly the dequeue is never enabled if its ready signal is not true. Okay, so we're building those together and still maintaining our original requirements that we can't call a method unless it's ready. Okay, so now I've taken this circuit and I've redrawn it as well, and the goal of this is to once again highlight that what we've got here is on one side I've got my my input wires, and so the input wires are the data wires that are coming in and my enables, these red wires. My output wires are the green wires and the data that is produced by either value or action value methods. Okay? And so just keep that in mind in terms of thinking about what your circuit should always look like. All right, so this was just, kind of a couple examples to get us started, and our goal is to ultimately be able to figure out what the circuit looks like for any kind of complicated hierarchical sequential circuit. Okay, so we've seen a picture similar to this one before, where if we replace these modules with registers, it was basically the definition of a single module. Okay, so what happens in a single module? In a single module, we instantiated some registers, and then we specify, what's the data that's going into those registers, what's the enable for each of those registers, and that's defined through this combinational logic of the method. And then we also have, inputs and outputs, which are specified by the interface of this module. So you can now go a step further and essentially build more complex sequential circuits by putting together a bunch of smaller sequential circuits. And so now you can think of each one of these modules is in itself a sequential circuit. And we can combine them all together in order to make a more complex sequential circuit, and we do it in exactly the same way. So how is this going to look? When I define my higher level sequential circuit, I'm going to have my state instantiation, which is going to say this higher level circuit consists of these modules, module 1 through n, and it's going to instantiate all of those modules. Next, it's going to have a bunch of methods and rules which are going to define the combinational logic, which is going to tell me how these modules both get updated as well as how they interact with each other. And finally, our interface is going to define the inputs and outputs of this higher level module. All right. So now what we're going to do is we're going to kind of start from scratch. So we saw a few examples in order to get a sense for how it is that we're building these ready and enable signals. And now we want to be more concrete about, actually being able to follow specific rules in order to do this in a routine manner. Okay? So the first thing is, as I've mentioned, every module represents a sequential circuit, and we know that we have a basic module that's been given to us or is made available to us, which is whose definition is outside of our language, and this is a register primitive. Okay, so the most basic module is going to instantiate registers in order to be a sequential circuit, and then higher level modules can instantiate both registers as well as other modules. Then our interface, as we've said several times, is going to define what our input and output wires look like. And the rules and methods are going to define what the combinational logic and how it looks like, as well as how to produce the enable signals for this more complex sequential circuit. And so the resulting hardware is going to in itself be a sequential circuit made up of a bunch of smaller sequential machines. All right, so first let's take a look at the interface of our primitive register. So we've already been using registers, but we've kind of been taking for granted what the interface looks like. So the interface of a register is that you can do both reads to it and you can do writes to it. And so officially, it's got two methods. It's got an action method, which is write, which is going to change the state of our register. And it's got a value method, which is this read, which is going to just return the current value of our register. Now, when we want to instantiate a register in one of our sequential circuits, the way that we do that is by calling this make_reg or make_regu method. And what this does, the make_reg allows you to instantiate a register and give it an initial value. Make_regu is simply going to instantiate a register but say that its initial value is undefined. Okay? Now, in the case of a register, our guards are always true, okay? So another way that we might picture this this image of our register module is that even though we actually officially, have these two ready signals, because they're always true, it's actually okay to kind of think of a register as just looking like this, where it basically has data coming in and an enable, and you know that the guards are always true. In addition, because the register is our primitive module and we use it so much, we actually have special syntax for specifying when we're doing reads and writes, and we've seen this already, which is that we use this double arrow to indicate that we're doing a write to a register, and so this x double arrow e is equivalent to saying x write expression e, and you can just say x instead of saying x dot read. Okay? And so we'll always be using the shorthand notation of accessing the methods of these registers. Okay. So now let's move on to the next step, which is our interfaces. And our interfaces, as we've said, define our inputs and outputs. And so let's be actually more concrete about exactly what kind of wires we're going to have given any particular interface. Okay? So what have we said? We said that every single method is going to have a ready signal. Okay? So that's always going to be true. Every method can also have some data wires. And so if you have arguments to your methods, you're going to have input data wires. If you don't have arguments, you're not. Every action method and every action value method have to have an enable wire, and so that's going to be this red enable that we're going to see in our modules. And then every value method and action value method produce a value, and so they're going to have output data signals coming out. And finally, an action method doesn't have an output, so there's not going to be any data wires coming out of our action methods. Okay? So if we look at our GCD example, we see that it follows all of these rules, right? Both our start and our get result have a ready signal. Because both of the methods are action methods, they each have an enable signal. The start method has arguments, and so it has input data coming into it. And the action value method produces an output, and so here we see the output. Okay? So just from the specification of the interface, we're able to draw this picture showing exactly what the inputs and outputs look like. Okay, so the next step is to figure out what my guards are. So we've said that, when I write a method, I can write an explicit guard associated with that method. But in addition to the guards that I write explicitly, if I'm calling other methods within my method, then I'm going to inherit the guards of all those methods that I'm calling. Okay, so when I try to figure out what the guard of my actual method is, it's not just the guards that I have explicitly specified, but in fact I have to put together the ones that I'm inheriting with the ones that I've explicitly specified. And so the compiler is going to do that for us. And so let's let's go back to our FIFO example, which we saw before. And so this is an example of explicit guards, right? So here we basically said for our NQ module, our guard is not V, and so that was a direct connection from not V. And for our DQ method, it was V, and for our first method, it was also V. Okay, but suppose that we now go to this more complicated hierarchical sequential circuit, which was our multi-GCD circuit, which itself instantiates several sequential circuits, right? So now we've got this GCD1, GCD2, which themselves have ready and enable signals, and then we have our start and get result of this higher level, which we need to produce, the result, the ready and enable signals for. So what does that look like? So if I look at the start method of my multi-GCD, you'll see that it doesn't actually have any explicit guards, right? But that doesn't mean that I can always call start, right? When would I not be able to call start in this multi-GCD? Or when can I call start? I have to have at least one of my GCDs not being busy, right? If both of them are busy, then I can't initiate a new GCD computation. Okay, and so basically this is an implicit guard which is going to be generated for us by the Bluespec compiler. And so what's actually happening here? Well, inside of our start method, what we're doing is we're calling GCD1 start and we're calling GCD2 start. So in order to be able to actually execute this method, it must be the case that the methods that I'm calling are also ready. Okay, and so explicitly what the compiler is going to generate for me is that if turn is 1, then it must be the case that if turn I is 1, then I'm up here, then it must be the case that GCD1 start ready signal is true. And if it's 0, then it must be the case that the GCD2 is ready to start a new computation. Okay, and so together, those are going to produce this outer level ready signal of my higher level sequential module. Is that clear to everyone? Any questions about how we produce that? Great. Okay, so the next step is, now that we know how to produce our ready signals, is how do we produce our enable signals, okay? So at a high level, the enable signals are always implicit, and so we need to figure out, you know, what is being implied in order to actually enable our different methods. And so the way that we do this is we're basically going to propagate enables that are coming into our methods to all of the methods that we're calling, but we're going to combine that with any combinational logic that's associated with the calling of those methods. And we're going to see explicitly how to do that right here. Okay, so let's take a simple example. Suppose that I have a method here which doesn't have any guards, and all that it's doing is it's taking this expression E and it's assigning it to my register X. So the first thing that I have is I've instantiated my state register, which is this register X, which has data and enable. And what I'm going to do is I'm going to have this method F, which has an expression E in it, and it's going to receive my A input. It's going to feed that into the E expression, and that's going to produce some output data, okay? That's what we'll call x.data. Now, when my F method is enabled, then I'm going to pass that method, that enable, directly to the enable of my X register. And so I'm going to take these two things that I produced and directly pass them as the data and the enable of my X register. Okay, so that case is relatively simple. Now, remember, just for, you know, to keep these not cluttered, I'm not showing the ready signal, which is always true in this case. Okay, so now let's take a look at another example. Suppose that I have a conditional here, where my method is not always assigning to X, it's only assigning to X if B is true. Okay, so what is that going to look like in my hardware? Well, once again, I have an X register, and here I have some combinational logic that produces my expression E, as well as my expression B. And what this is going to do is it's going to say, well, the only time that I'm going to allow writing to X is if both F enable are true and B is true. Okay, so it's going to take that logic and combine the B signal together with the F enable in order to produce the enable for my register. Does everybody see why that should be done? Yes? Okay, so now let's take a look at yet another example. Suppose I have an if-else statement, right? In this case, I'm always writing to X, right? I'm writing to X in the if statement and I'm writing to X in the else statement. But what I have to do here is I have to select which one of my expressions is the one that's going to control what's written into X. So how do I do that? I use a multiplexer, okay? And so I've got my logic for computing expression 1 and expression 2, as well as my conditional B. And now the result of that conditional B is going to control which one of these expressions is going to feed the data into my X register. Okay? And in this case, I'm always going to write to X, and so my X enable is just going to be directly connected to the F enable. Any questions about this? Nope? Okay. So the last example I want to show you is, suppose now that we have two methods trying to write to X, okay? How are we going to, in the hardware, make sure that we don't have this problem of double writes, right? We can't have two things writing to X at the same time. And so we already know, that we can compile the expression 1, we can compile expression 2, but we somehow have to select which one of those is actually going to feed X. And this is where our special multiplexer comes in, where we have two things that could potentially be updating X. And so we have the enable for F controlling whether we pass the F signal, and the enable for G controlling whether we pass the G signal. And it's the compiler's job to make sure that at no point in time are both F enable and G enable set to true at the same time. Okay? So the Bluespec compiler is going to do this for you. So it's going to make sure that if you have such conflicts, that it's not going to allow them to be scheduled at the same time. And the way that it does this is by defining what we call a conflict matrix, okay? So for every time that you have the ability to perform to call multiple methods, you want to try to analyze whether or not there's a conflict between these methods and they can't actually be executed at the same time. So in order to understand how that works, we're going to start first by looking at the conflict matrix for our registers. So here's the conflict matrix for our registers. So what is this thing telling me? Well, I've got rows, which corresponds to my methods, and I have got columns, which corresponds to my methods. So the .r is my read method, .w is my write method. And so what is this thing trying to say? This box right here in the upper left is saying, can I do two register reads together? Okay? So is there a problem in doing that? Will I have any, get any bad data if I read the register from two different methods? No, right? So this is what we call conflict-free, and so we label this CF, meaning that it's not a problem for both of those reads to happen at the same time. However, if I try to write to my register from two different methods, I will have a problem, right? This is a double write, which is not allowed, and so this is labeled as a conflict, and those two things cannot occur at the same time. What about a read and a write? You'll notice that these tables are basically symmetrical, so this box is really saying the same thing as this box. And what this is saying is that we can do reads and writes together, but the constraint is the following, which is that when we do a read and a write at the same time, the behavior is as if the read happened before the write. And that's what this less than sign right here means, okay? So CF means it's conflict-free. We can do two reads at the same time. C means that there is a conflict, meaning we cannot do two writes at the same time. And this less than means that we can do a read and write at the same time, but the behavior is as if the read happened first. So in other words, if I'm reading from register X2 and I'm writing to register X2, the value that I read from X2 is the old value, not the new value that I'm about to write to it. Okay? All right, and so then we use this conflict matrix of a register in order to build up conflict matrices for all of our modules. And you can also basically build conflict matrices for rules as well. And so we're going to finish off today by just looking at our one-element FIFO and trying to think about what the conflict matrix for this one-element FIFO looks like, right? So what are the methods that we've got? We've got NQ, DQ, and first, and we want to get a sense for, which combinations of these methods could actually be executed in parallel, okay? So it's a one-element FIFO. So can I do two NQs at the same time? What would that mean? I can't, right? I can only NQ one thing into my one element FIFO at any point in time, and so there's a conflict if I try to do both NQ, two NQs in parallel. Similarly, if I try to DQ two things at the same time, there's also a conflict. But what about if I try to call first twice from two different methods? Is there a problem with two different methods reading the value that's currently in my one element FIFO? No, right? So that's considered conflict-free. All right, what about the rest of these boxes? Well, there's a situation here where NQ and DQ we've labeled as ME. ME stands for mutually exclusive, and what that means is that if you look at the explicit guards for the NQ and DQ methods, it's never possible for them both to be ready at the same time, okay? So because they cannot be ready at the same time, that means they're mutually exclusive, and we don't actually have to worry about conflicts between them because there is no possibility of calling them at the same time. So just like the DQ and NQ methods are mutually exclusive, also the NQ and first methods are mutually exclusive. So the last situation to think about is DQ and first. Well, it's perfectly fine to do DQ and first at the same time, as long as we treat it as if first happened first. Okay, so if I'm doing a first and a DQ and I treat first as happening first, then what I'm doing is I first get that the value that's in my FIFO, and then I DQ it, and it's perfectly fine for both of those calls to be done at the same time. And as I mentioned, for mutually exclusive situations, we don't actually have to worry about it because those conflicts are never going to arise. So next time we're going to continue with more on conflict matrices, and just to get you guys thinking about what we've learned today, we are giving you this take-home problem, which is to actually draw out the full GCD circuit of the basic GCD, not the multi-GCD, okay? So we've shown you here the interface. We want you to actually figure out what are all of the internal signals. And you can assume that you have as black boxes, you know, some module that does subtraction and another module that does comparison, for example, when doing this problem. All right, that's it for today. Thanks, everybody.